Well, good evening, everybody. Welcome to the November meeting of the Ottawa RASC. Looks like we got a pretty good house here tonight, and that's good because we a little bit of a departure from our usual format. We haven't got as many talks, but we have one very long talk, which I think you're going to find fascinating. Our friend Simon Hamner has come to give us a really interesting presentation. I won't let the cat out of the bag or anything, but needless to say, I think you're going to enjoy that. So it's fairly long, and we want to give Simon plenty of time to go through it. So I'll just step through quickly what we've got on tap before that. Then we'll do Simon after the break. But to begin with, we'll have Gary Boyle come up and talk about Ottawa skies, his usual segment there. Al Scott is not with us tonight, but he did supply us with a short video. So I'll just talk to that when that comes up there. And then Chuck and Jillian had a little exploration adventure. We tried to get Chuck up last month, but ran out of time there. So we're going to give Chuck another shot here. But I'll be watching your time there, Chuck. You know that, eh?
I know.
Yeah. Okay, that's good. Then we've got a couple of observations. We'll have a quick break and do our door prizes, and then we'll jump into Simon's talk on the solar system. All right. So, Ottawa members in the news, we've got a couple. This is I don't expect you to read all that, but an article submitted by Al Scott to the Empire EMC on light pollution. So it was published talking about reducing light pollution and the cost of illuminating the sky needlessly. So how to go, Al? There, he's fighting for clear and dark skies for us. And there we go. The other member is Jacob Von Chorus, who got a rather nice image published, which we showed a couple of months back there, his image of the Pac-Man. And yeah, you can see it's enlarged actually on the top right-hand corner. So is Jacob here tonight?
Yes, he is.
Is he? Okay. Nice piece of work. All right. And without further ado, Mr. Boyle. Baton of power. Okay, you're good.
Good evening, everyone. Welcome to the November meeting, just to March 4th. You get to do some early winter observing now with Orion rising around 10 p.m. Jupiter is nice and high. Just other than the same old M42, of course, there's M1, the Crab Nebula. We can move on to that one. The Crab Nebula is 6,300 light years away. Well, it's off the side here. There's a couple of zeros, but on my screen it is. Magnitude 8.6. And it was seen on the night, or I guess the night or the day of July 4th, 1054 AD. And in fact, it outshone the moon for 23 nights. It was so bright. So astronomers have estimated that the power released from this one star equals 400 million suns worth, and any planets within 50 light years would cease to have an atmosphere because of the radiation and bad stuff coming off the stars. So it's a good thing this puppy's a little far away. Next slide. Other than that, then we'll go down to NGC 2264, which is what, Gary? What object?
The Cone Nebula or the Christmas Tree Cluster.
And?
Rosette.
No, Cone, Christmas Tree, and?
The Foxfur Nebula.
Foxfur, that's it. Very good. Give Glenn a round of applause, folks. He knows this stuff.
The next one's below.
Cone, Christmas Tree, and Foxfur. The Christmas Tree is the actual cluster. The Cone is over here, and the Foxfur is down here. It's a very wide nebula. Observe, of course, in a telescope, but photography really brings out the subtle array. Next slide, please. Last month, we mentioned a couple of bright comets in the sky. Comet P168, or 168P, Huygens-Rother, has really gone to outburst. And here we have the top left star of the square of Pegasus, or which is Alpha Andromeda also. So it's almost overhead. It's between 9th and 10th magnitude now. When it went to outburst, it really got bright to about maybe 8th magnitude by the end of September. It's getting a little fainter now. So again, get on Google and double check to look for this chart and try to find it. So we should be about here right now in the second. Okay, next slide. And this is the comet that we were just speaking about. You can see that it's actually broken apart. So that's what's causing the outburst. New material being released to the sun. But will the comet survive? Will it break apart more and just fizzle out? We're not sure. Okay, next slide. For those that have a lot of money and can get a booking, we have a total eclipse of the sun, November 13th, just about 4 minutes worth of totality on the 11 days from now. And you can see red star right over the Pacific, but partly over Australia. Next slide shows a more detailed area. So if you can get within here, you're lucky. So, and 2 weeks later, we're going to have a penumbral eclipse of the moon. But unfortunately, penumbral is only the exterior of the moon. So photography, pretty well, you can see when the moon's just turning that little shade of dark. So really nothing seen from here, unfortunately. But they pay me the big bucks to advertise. I'm advertising. And next slide. The Eleni meteor shower, which, well, but about a decade ago was a storm. But 2,000 per hour is a phenomenal display that I saw at Mike Worth's in Perth. But unfortunately, we're down to only 15 meteors per hour, seen by a single observer. Here's where the radiant is, just in the sickle of Little Lion. But hopefully the storm will come back in a few more decades. But always observe, you never know. Mother Nature could throw a curveball, but for now, the thread or stream that Earth is passing through is really not populated too much. Next slide. On the 27th, I forgot to put the date down here, the 27th of November, you'll wake up to Venus and Saturn very close in the eastern sky before sunrise. So on the 27th, it's on one side, and then 28th, Venus is on the other side. So pick one or the other because we have such fantastic weather, it's always guaranteed. Next slide. On the 22nd, Jupiter will have one of its many transits of satellites around it. The 4 main satellites are Io, Europa, Ganymede, and Callisto. Going through the models, a lot of the observations are during the day on our side of the Earth. So the only decent one is still at 1:59 in the morning of Io. So I have the shadow ingress and shadow egress. Shadow ingress is when the shadow first appears on the edge of the planet, then followed by another 18 minutes later, then the actual moon itself can be seen against the background of Jupiter. Then we have shadow egressing, and then after transit of the satellite egressing after that too. Next slide. And let's not forget this weekend, fall back 1 hour, and 2, when you're converting, don't subtract 5 hours from universal time for any major events in the Observer's Handbook. Okay. And here's just the synopsis of the various planets. Pick your favorite. Of course, you know with these two guys, they never move. Everybody finished with the planets? Next slide. And the lunar feature. We have the beaver moon. I don't make it up, I just report it. And it's the smallest beaver for 2012. Because it's furthest away, because the furthest the moon can be from the Earth is about 406,000 kilometers. And that's about it for the observations. See you next month. And last but not least, the last opportunity to purchase tickets for the annual dinner. 2 weeks from tonight is the dinner. So I really need to have people buy tickets or give me a check or commit something by next week. By the week before, I must give a definite number in, and we only have 34 tickets sold as of now. What? So 34. So 34 tickets are sold. Pretty low, pretty low. I don't know, but we usually have about 60 or 70 people that show up. I'm getting a lot of door prizes coming in. There's binoculars, eyepieces. It's a good array of door prizes coming in, but just truly the meal is worth the price itself. Same price last year, $42 per ticket, cash or a check made up to the Ottawa Centre, RASC. And Dr. René Racine from the University of Montreal will be speaking on the quest for extremely large telescopes. And it should be a fun night, as we always have. So other than that,
what's the date of it?
if you come back one, please. November 16th. I think one more. Yeah, November 16th. 2 weeks from tonight. 2 weeks from tonight. And the same old cocktail at 6 p.m., dinner at 7, hippa beef. The food is just phenomenal. If you've never attended the annual dinner, the food, like I said, is just worth the trip. Very, very good. Because these are all second and third year culinary students from Algonquin, and it's quite good. Plus, we all get to enjoy conversation other than astronomy, could be politics, whatever. How well the Maple Leafs are doing. It's great. The Maple Leafs have not lost one game yet. I love it. I love it.
Door prize for the night.
Okay, great. And we have one extra door prize for the night. Thank you, sir. This is donated from
Me.
from Chris Tarrant. Thank you, Chris. Door prize for tonight.
Read it.
Oh. Back in my day, we had 9 planets. Oh, funny. Wait. Is it my size? What size is it?
Extra large.
Extra large. Yes. I'm going to get 4 tickets.
It
Thanks.
shows up on that table and I get 2 weeks.
It's on the floor. It's on the floor. Okay, thanks, folks. See you during the break for ticket sales if you have. Thank you.
Wasn't there some rumor, Gary, about a car or something? Door prize? Was there a rumor about a car?
About a what?
A car door prize? I remember hearing something. I could be wrong.
Barhaven. Somebody wants to go to Barhaven and have an observatory ready for a telescope. Just a plug, just a plug.
Yeah, it's a 2006 Saturn.
Offer it up as a door prize. Huh? Huh? Who needs an observatory? Hands up. Huh? There's a few there. It's an opportunity for you, Gary. All right. All right, as I mentioned, Al isn't with us tonight. He had a previous engagement, but he did send along this rather interesting link to a video which we downloaded, and it goes back to the Venus transit there. As you recall from the talks that we had, one of the reasons that one of the principal reasons that the Venus transit was so heavily studied in years gone by was that by accurately timing the passage of Venus across the disk of the sun, we could work the math and figure out basically the size of our solar system and the orbits and such, which we really had no other way to do that. And we use a technique called parallax with that. And this video was filmed by a couple of individuals there, and they've put the information together. One was filmed at very high northerly latitude. I think it was Norway or something. It was like 78 degrees north latitude. And the other one was imaged at 35 degrees south latitude, so quite a wide spread in latitude there. And if you watch the video, actually you can probably let it run there, Chris, because there's no audio for this. Have a look at the top 2 rows. The top 2 images are from the northern environment, and the bottom 2 are from the southern environment. On the left is white light, on the right is hydrogen alpha. But the important thing to note is have a look at the difference of positions of Venus there as it transits across, and you'll see, have a look at, especially now, you can see this at the southern position, right? So this is exactly the type of thing that they were trying to determine with some sort of accuracy, and one way to do it, sort of an additional bit of data, was the timing of the ingress and the egress there. So, but that really brings it home. You could really see the difference just on being on different parts of our own planet. So I'll send that along there. I thought that you might be interested in it as a sort of a cap to our talk about Venus transit. And that's all we have for that today there. So hope you enjoyed that. All right, thanks, Alf. All right, Chuck. Chuck is going to talk to us about a hole in the ground. Oh, damn, I let it out of the bag, didn't I? I'm sorry.
Here we are in a hole in the ground.
There you go, sir.
Thank you. A little hole in the ground, a lot of science with it. These hunters knew about this for years. It was just a place where they met. They actually found deer drinking out of it. And it was only a couple of years ago that one of the hunters noticed some metal objects around the rim of the crater and brought it into Dr. Hurd at the University of Alberta. And through that, they've documented, yes, in fact, it is an impact. It happened 1,130 years ago, plus or minus a couple of years. And the reason they know that is the carbon-14 of the charcoal buried by the ejecta. The dimension, 36 meters, 6 meters deep. And I give you an idea of the scale. You can see Jillian and I sitting down in there having a good time in a crater. Let's see if this works. There we go.
You sure know how to show a girl a good time.
Hey, I'll tell you. I'll tell you.
What happens in the crater stays in the
Not anymore.
Not anymore, yeah, we got it on film.
It's all on film.
So where it is, this is Alberta, Edmonton, and Whitecourt is just to the northwest of Edmonton. And the crater itself is 20 kilometers or so just south of it. These are tracks that I made with my personal locator beacon on the airplane. And we circled the crater, and I'll show you some pictures in a bit. But as I mentioned, there's lots of science with it. It is a brand new crater that has meteorites around it. It has an ejecta blanket. The crater is well defined. It has a raised rim, and there were shock indicators, planar deformation features in some quartz that they found. The bolide itself was about 1 meter across, and we'll get into that later. As I mentioned, there's lots and lots of science to do with this one. Some dimensions, you can see the contours and so on. And this image here is with the technology LiDAR. The crater was not discovered by LiDAR, but the crater was used to calibrate LiDAR, and I'll get into that as well. The ejecta blanket, you can see the black in these diagrams here with the various directions of plotting the ejecta and so on. As I mentioned, the date of the crater was found by the charcoal buried underneath the ejecta, and it is fairly true that, yes, it's about 1,130 years ago-ish. The bolide itself, it impacted at an angle of about 40 to 55 degrees-ish, they suspect, and it came in from the southwest. The meteorites itself that we found were found to the northeast of the crater, most of them, but you can see there's meteorites all over the place. And there's a fantastic tale about these meteorites we'll get into in a second. The square around it is a restricted area. You are not allowed to collect meteorites within that. And part of the GA was a meteorite collection, and Jillian will describe that. But I personally thought, the place is going to be hunted out. There's not going to be one left, but you'd be surprised what we found. So, without further ado, I'll introduce my crater explorer, Jillian Sullivan.
Hi, I'm going to talk more about the tour that we took of the crater itself. This took place this past July 2nd, the day after the wrap-up of the 2012 RASC General Assembly in Edmonton. This was a rare opportunity to visit the crater, which is a well-hidden gem, and we were lucky to be among the 30 who registered for this full-day adventure. After a 2-hour bus ride northwest from Edmonton to the town of Whitecourt, we began with an excellent presentation by Dr. Chris Hurd on the crater. Then it was off by bus again, until the road got too rough. The tour description had stressed that we needed to be in good shape and able to walk up to 90 minutes in rough terrain. Here we are at the start of our 3-kilometer hike into the crater site. Okay, the road soon turned into a hiking path, and our Nordic walking poles really came in handy. The organizers had arranged for a set of ATV shuttles, which most people used. An article published in the Whitecourt Star newspaper about our tour noted that due to the precariousness of the ride up, directions are not given out to tourists. So we really felt we were about to see something that very few people have a chance to see.
I just want to mention, too, that Jillian and I were the only people that actually walked both ways. Everybody else took the buggies. I just wanted to brag about it.
Hey, Chuck, who took the picture?
You're
only two.
No, there were lots of us.
Oh, you'll see in a second how many.
So here, this is the impact site, believe it or not. It's taken from one rim, with the far rim about 2/3 of the way up the photo. You can see the bottom of the crater where there's bare soil in the middle bottom of the photo. Obviously, it's pretty much obscured in the leafiness of summer. It's much more visible in winter, but I'm glad we were there in summer. Next slide. Here's Chris Hurd standing just below the crater rim, explaining the direction and angle of the meteorite as it hit Earth. Chuck provided the technical title.
Yeah, you can see the steepness of the crater too. It's very steep there.
Yeah. This gives a sense of the crater size with tour members ranged along the crater rim. This was taken from down
It was Jillian and Julie.
inside the crater. Okay, descending down into the crater. Finally, we got to go down and check it out. It really felt quite something being down in the bottom, looking out of it. Once we got next slide. Okay, here we are at the bottom, and Chuck used his GPS to mark the exact location so that we could look for it later by air, see if we could find it. Next slide. With the crater tour part over, we broke into small groups led by local experts to look for meteorites. This was, of course, outside the restricted zone that Chuck showed you a bit earlier, the area that you're not allowed to look for meteorites in. For a couple of hours, we had the use of metal detectors and magnets, and here the detector was whining loudly, so we knew we had something. Success. The last step of looking for a meteorite can be rooting around in the soil with a strong magnet, like the one here. You can see there's a small meteorite clinging to the head of the magnet.
I was amazed. There's wall-to-wall meteorites there.
We were lucky in that our expert, the fellow there in the sort of the gear in the middle, had scoped out the area before, so we'd actually found some things in advance. Not everybody had that advantage. Okay, so here's another spot where the metal detector was going wild, and here's the result. 3 small pieces of meteorite. We should mention that our metal detector and magnets also located a number of nails and wire, a legacy of the long-gone homesteads in the area. Our little group was fortunate. Other groups found less or nothing at all. So we felt very good.
It's not the size that counts, eh, Jillian?
Moving right along.
Moving right along.
After a long day of crater exploration, there's nothing like a cold one at the White Court Casino. It was a day of contrasts. It was unbelievable, from a crater to a casino to back to Edmonton. The man at right is Murray Paulson of the Edmonton RASC, and a veteran White Court meteorite hunter. He has found hundreds, and much larger than what we found. He also took care of the logistics for the tour, which went very smoothly. And while at the casino, tour members had a chance to meet the mayor of White Court and other dignitaries, and we all received golf shirts to commemorate the occasion. It made quite a fuss. It was very nice. The whole thing was very nicely done, and we arrived back in Edmonton late that night, tired and elated. Now back to Chuck and the magic of LiDAR.
Okay. Yeah, stand back. We're going to do some science. They mentioned that the LiDAR was actually calibrated with this crater, and you can see this is an aerial shot of the area of where the crater should be. It's right there, actually. And with trying to think of the word here, the processing that they use, they can actually attenuate the noise from the images and just have the ground reflections. And using this technology in this crater, they've calibrated, and they've probably they're using it quite a bit now in other areas. Well, I don't think they found any other craters, but it's quite a strong technology. That is a computer drawing from the data of the LiDAR, and you can see the shape. The meteorite again came in from this angle, and the meteorites that we found were in this area here. And again, for the record, we were outside the magic box. The crater itself, now, is very, very unique in the fact that I mentioned that it was a 1 meter wide bolide that caused the crater. Now, there are meteorites that we know of that are tons, a couple of meters across and so on. So here's what we're looking at. We're looking at various sizes of meteorites that arrive at terminal velocity going thud versus cosmic velocities which go to an explosion which caused these craters. And again, it's the explosion that caused the crater, not the impact. Basically, it's the energy transfer from the mass times velocity squared that causes the explosion, which causes the hole in the ground. So what we have is an example now of the minimum size, minimum velocity of a mv squared type crater. And Dr. Hurt's pretty excited over this, and we might have some more in papers about this in the future. Aside from the meteorites themselves, what I'll get into, first of all, Julian mentioned I got the GPS coordinates. We stood in the center and I zeroed the GPS and flew over the area, and lo and behold, you can see it there? I couldn't see it either. So what I did, I just set the GPS up, put it under the wing, and took a picture and hoped for the best. So, give up. There it is. So you can just barely see the clearing in the bottom, and this was the rim that we walked down. The area that we found all the meteorites was around here. And again, there's lots to be found there. But to get in the air and look for it, it's impossible unless you know exactly where it is. Now, as far as the bolide itself, now, when the impactor happened, it was going about 10 kilometers a second, so that's below the escape velocity of this planet. I think it's around 12 kilometers plus. So essentially it had slowed down in the atmosphere, but not slow enough not to prevent an explosion. But what had happened is that parts of the bolide did come apart in the atmosphere, hence the meteorites that we found, which were typical meteorites with the little indentations called regmoglyphs in them and so on. The meteorite that broke off the bolide on the explosion was a different kettle of fish altogether. You see the difference here. This is a typical meteorite that came through the atmosphere, slowed down to terminal velocity, and goes thud on the ground. Whereas this one here, it's like a shrapnel from an explosion, basically. And it came off the bolide during the explosion. And it didn't have the typical indentations and so on. It had basically just like a metal that broke off from an explosion of a metal object, basically. And so these are very unique. I don't think there's any other example anywhere else that we found. And fortunately, I've been able to grab that one. And as well, Dr. Hurd, from studying the Widmanstätten patterns within the iron meteorite, he has determined that the bolide came from an object or an asteroid about 50 kilometers across. It's 4.5 billion years old. And just by the ratios of the nickel in the Widmanstätten there, he calculated that this meteorite-specific bolide that hit had cooled at 50 degrees Celsius every million years. So from that, they estimated that the bolide was, or the asteroid itself was over 50 kilometers across. So, as I mentioned, lots of science with this one, and it was a very exciting trip. We had a great time. And as we say, what happens in the crater stays in the crater. So we always finish with how bright and beautiful a comet is as it flies past our planet, provided it does fly past it. Thank you.
Chuck, I had a question.
Yeah.
I'm just wondering, that looks like a very small impact compared to what we're normally...
Yeah, if you remember a couple years ago in South America, there was another one about the similar size. And we suspect that was an mv squared type explosion that caused the hole.
So that small crater is very rare.
Exactly, and that's what I meant by the science in it, in the fact that there are bolides that or meteorites that are larger than that are found, whereas this the size of this that caused this crater was only a meter across. So the very acute angle that it came in, maybe it was slower than other ones, maybe it impacted the Earth, catching up to the Earth versus, impacting head-on. All kinds of variables like that. But yes, this is a very unique crater, and that is so small, but it still is, in fact, a crater from an explosion. Kind of cool.
Chuck?
Yeah.
Actually, I'm wondering, Chris, can you back up a few slides? There's one thing I noticed on one of the slides that was the LiDAR, right up at the No, you had it.
This
There.
one? Yeah.
So at the bottom, up at the top right-hand corner there, it looks like there's another indentation there, much smaller.
You know something, I never noticed that before.
There's something for you to explore.
Well, we'll just have to go back and look at that, Jillian.
That would be the O'Dale Cloninger crater. Yeah.
Well, the Cloninger O'Dale crater, I'll give it to you. That's a good point. Holy Mackinac, look at that.
Seems like a little pit out in the middle of nowhere.
I'm going to email Dr. Hurd about that.
There's another one there too.
Yeah, just below it.
Right in here, yeah. So that,
Just to the left. Right.
oh, there it is, yeah, right there. Oh, yeah. So it's in this area. Holy camole.
Belly button.
Guess you'll have to go back.
We're going, that's it. We're going back.
Doctor, another question.
Yeah, sure, Chris.
What makes you say these are so rare? Because people's perception of such a small hole wouldn't be of a meteor crater.
That's true.
Tons of these.
There are tons of these. There actually, if you look at my website, I've got tons of these kind of holes in the ground that are documented, that are sinkholes, all kinds of different geologic processes that cause them. But the fact that it's got meteorites around it, there's impact planar deformation features, the impact itself caused those things. Yeah, it is very rare. But to answer your question, that's what science is all about, is finding out what's going on here.
Jeff, was that classified as, what was it, a coarse octahedrite or what?
Got it on the website. I can't remember now. Say the question again, Brian.
Was it a coarse octahedrite? So I'm just looking at the witness set and figure.
Yeah, it's an iron. I didn't write it down, or did I? Just a minute. Did I write it down? Did I write it down? No, I didn't. I didn't want to get too technical. And Ron's not here, so he'd know. It's on my website, guys. Just look at there, I guess. Sorry about that, Brian.
Now, Chuck, could you explain that formation over here, too?
Which one's that?
There's what appears to be a hole here.
Oh, yeah, there's
A hit. Would those be hits?
No, these, that's a creek here. It's a creek, and there's all kinds of dried up creeks.
This formation right there.
Yeah, there's all kind of dried up creeks around there.
On the moon, there are sometimes multiple hits right in a row.
Yeah. Sometimes impacts happen, and then you have the blump, 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 blump from the impact, yes. And of course, there's the Clearwater craters up in northern Quebec that are two meteor craters, lined up in a row from a twin bolide. So, yeah, I'm sure that was pretty obvious. So, but I'm going to ask Dr. Hurd about that one. I'll get back to you guys on
I
that
think
one.
that was in the line of the ejectable pattern
Yeah,
as well.
exactly, because it came in like this. The meteorites are all here. So the heavier one would land first and the lighter ones later.
That's right.
Woo. I think Ottawa Center's got something going here. Anything else? Thanks a lot, guys.
Lots of fun. That's interesting, actually. I have a bit of a dovetail to your thing. I was going to mention it as part of my observations there, but I'll mention it now since it follows on the heel of your observation there, or your talk. 17 days ago, I was out doing some imaging, and I'm out about 20 kilometers past Almont, to the west of Almont, and at 1:05 in the morning, I saw the most brilliant bolide I'd ever seen in my life. I saw it come from the south, from about the south or maybe the southeast. I picked it up at about 30 degrees elevation, rocked overhead at about 55 degrees elevation, and I lost it in the trees in the northwest at about 25 degrees elevation. And that took about 2 seconds, so it was boogieing. And I thought, well, that's really cool. I wish I was actually imaging, but with a telescope and in a much smaller piece of the sky. Anyway, I went back to my work there. 3 minutes after I saw that, I heard double sonic boom. It's the first one I've ever heard of all the observations, and it's dead quiet out of my place. There was like no other noise. I was sitting down doing my stuff, and I just hear like a, and it was definitely from that direction there. I sent in a report because I figured with the timing in that was probably about 60 kilometers away from me where the boom itself was generated, and looking at the path on the map, I figured if it survived passage, that it sort of passed between Renfrew and Pembroke and might have landed on the other side of the river in Quebec. But I haven't heard back anything from that yet, and I was going to put it out to the members there to see if anybody else was out on that night. I think it was Tuesday, October the 17th, if memory serves.
I'll send you a
105.
website of reporting objects like that.
Okay, I can. I sent it to a gentleman down at Western University who operates the All Sky Camera Network.
Okay.
But I haven't heard back from him. Anyway, just thought I'd mention that too.
How about the observatory at Buckshot Lake or up
Yeah, I
Galadar?
haven't heard anything at all.
But they might have.
They might have picked it up. Yeah. I'll ping them again there and see. But yeah, just thought if anybody else had happened to be out at that time. It was brilliant. It was brighter than the full moon when it came down, so it was rather interesting. Okay, observations. Actually, we're a little bit light this month. What's the matter? Has it been cloudy? Oh. Come on, guys. All right, first up, Gordon. Gordon and Julia, actually. Actually, if memory serves, Julia is going to give the presentation. Oh, there we go. Hi.
Hi.
Get here, let me pick you up here. Okay. Up you go. Okay, so Julie and I were out observing the moon a couple nights ago, but about 2 weeks ago. And what did we look at?
Clavius.
And which crater is this that we looked at?
Plato.
Plato. And the second one you said was?
Clavius.
And what's the difference? What does Plato like?
Smooth.
And what about Clavius? Can we see Clavius, please?
Clavius was bumpy.
And what were the bumps?
They had 3 craters.
That's right. Very good. And then, okay. And then 2 nights later, I went out. This Clavius sketch is done just graphite on white paper. Excuse me. But I've been trying some new stuff. Can we have the next one, please? And this is with white pastel on black paper. I got treed out before I could get it to where I wanted it. But anyway, it's, whoops, which one do I want?
Center button.
Center button here. Okay, so this is Rost and Roste and Schiller. So, just a new technique I'm trying. Thanks.
Well, thanks, Gordon and Julia. I've only got one image for you this month. This is one I, I shot in the late summer there. It's the eastern half of the Veil Nebula. The Veil is a supernova remnant in Cygnus. It's quite large. It's the supernova. Interestingly, we were talking about the crab and its detonation. This is believed to have detonated approximately 5,000 to 8,000 years ago. A little bit uncertain on the time there, as we are in the distance, but recent estimates put it at about 1,500 light years from Earth, so substantially closer than the star that generated the crab explosion. But this is a very large complex of gas and dust from the explosion. It's the full extent of it, when you look at the east and west, is about 6 degrees, or about 3 degrees or so, which makes it about 6 times the diameter of the full moon. So this is only the eastern portion of it, but yeah, very photogenic object, and that's a 90-minute exposure, a total of 9 10-minute subframes there. So.
What were you imaging with?
That was with an Orion Starshoot Pro CCD camera on an 80mm refractor. So, and that's all I've got for you. So what we're going to do, Chris, you wanted, I'm next again. Oh, that's right. Okay. Yes, thank you for the reminder. Before we take our break there, I wanted to remind you again to submit any observations that you have. We're going to be awarding the 2012 version of the Paul Commission Observer of the Year award at the dinner. And so if you want to be in the running or know somebody that should be there, I need the data. So send me the data, and we'll have a look at it there. And absolute drop dead deadline for that is November the 11th. So that's coming up quickly. So please, if you do want to be in the running for that, send me your observations. Up next, Simon Hamner, and I'm going to run to the back and start my video camera because I'm taping too, Simon. Thank you.
Oh, great! I get to check whether or not it was all done properly. Let's see where I'll put those. Is that for me to tape myself? You know, Julia is going to be a real difficult act to follow. Not only did she get her astronomy right, but she's a lot cuter than I am. but I'm going to do my best. I just don't have those eyes, you know? All righty, let me just make sure I can do that bit good, and I can trust Chris to actually move us through. Okay, title of today's talk: Is our solar system and the Earth within it normal? You know, NASA really is the true master of public outreach. Thanks to its multiple websites, the general public and the media, are now pretty savvy about astronomy. So it came as a great surprise to me over a year or so ago to realize that no one in my several rather broad amateur astronomy circles seemed to know that October 2010 to August 2012 had been declared the year of the solar system by NASA. By the way, that's their website for the year of the solar system. So I decided that I had to do something about it, at least locally. And I gave a set of talks here at the RASC Ottawa Centre on various aspects of the solar system, focusing on our moon, Mars, and Venus. But now, as we've gone by a formal end of the year of the solar system, I thought it would be a good idea to take more of a global, or should I say universal, look at our solar system, with a view to addressing the following question: is our solar system normal? Currently, modern astronomy is turning up scads of exciting evidence in support of the notion that the universe is likely teeming with exoplanetary systems around stars by the billions of billions. At the same time, professional astronomers and planetary scientists are busying themselves seeking rapid and sometimes, quite frankly, shoddy comparisons with our own solar system. And even the local media are now talking about super-Earths and habitable zones, the potential for water, and therefore the potential for life. Now, much of this astro chatter is based on the assumption that our solar system, the one we know best, represents a fundamental model to which exoplanetary systems can be compared. And this implies that our solar system is therefore normal, that it represents the rule, as opposed to the exception. But does it? So tonight I want to address three fundamental questions regarding our planet Earth and its place in our solar system, in our galaxy, and in the visible universe. Now, as you can imagine, this is a pretty ambitious undertaking and explains why this talk is going to be longer than my usual 20-minute vignettes. And these questions are, and we'll come back to this: is our planet really representative of a habitable world in a planetary system? Is it a blueprint? Or is it a special case? And the second question is our seemingly tranquil and stable solar system really representative of planetary evolution? And again, is it a blueprint or is it a special case? And finally, the third question, is our galaxy representative of galactic environments within this universe as we know it? So let's start with the big picture first, and then we'll close in on our home planet. Next one, please, Chris. So, how normal is the Milky Way? Next one, please. Now, this is a fundamental question to be asking because galaxies provide the first-order environments in which planetary systems will evolve. Our galaxy is a pretty quiet backwater by galactic standards. It's a large, multi-armed, barred spiral with a supermassive black hole at its center, but luckily for us, that black hole is not very active, at least not right now. But many other galaxies have extremely active galactic centers that generate copious amounts of gamma rays, X-rays, cosmic rays, and ultraviolet light, none of which bodes well for a habitable planet. Next one, please, Chris. Many galaxies are seen to be interacting with their neighbors. In fact, cosmologists tell us that this is how galaxies grow and evolve. Currently, our galaxy is quietly digesting a number of dwarf galaxies that it assimilated several billion years ago. And it won't interact in any material way with the giant Andromeda galaxy next door for a few billion years to come into the future. So here we are, thinking about this at just the right Goldilocks moment in our galaxy's existence. By the way, when galaxies interact with each other, the resulting fireworks are not so much due to stars colliding like billiard balls, it's the exchange of interstellar gas that gives rise to a burst of new star formation. And the release of all that radiation associated with that star formation, which could make things a tad uncomfortable for potentially habitable planets in the vicinity. Next one, please, Chris. That burst of star formation can go on for quite a long time after galactic interaction, as can be seen in this well-known image of M82, long after it's thought to have had a close call with its nearest neighbor, M81. Next one, please. So my take-home message on galaxies is this. If you had to choose a galaxy to live in, I'd highly recommend staying put right where you are in the Milky Way. But just how much do we know about what goes on in the Milky Way, especially with regard to what's happening around stars other than our own sun? Next one, please, Chris. Until recently, this was the standard model of the standard astronomical model for the formation of planetary systems. Basically, a rotating cloud of gas and dust flattened into a protoplanetary disk around a central star, all of which then evolved by various predictable processes into a planetary system looking very much like our solar system. Next one, please. One vision of this planetary system model has been this planetary system model has been illustrated many times from many perspectives. In fact, note where a Jupiter right here in this artist's impression sits exactly where it should be, chez nous. By the way, most recent modeling suggests of observations of extrasolar planetary systems suggests that Jupiters like this at a great distance from their central star are actually very rare. Next one, please, Chris. But just how much of our own galaxy have we actually examined for exoplanetary systems? Well, it turns out to be a pretty small sample at the galactic scale. When I picked up this slide from the internet, and this is still the most attractive slide for this part of the talk, at that time, only a distance of about 300 light years from our sun had actually been examined for extrasolar systems. Today, this slide should really be updated to represent about 6,000 light years. But remember, our galaxy is 100,000 light years across. So we've only really looked in our backyard. Next one, please. But even within that small sample, astronomers have made some really interesting discoveries. At the galactic scale, astronomers already know that many stars, perhaps most, are binary systems of two stars orbiting each other. In addition to planets around single stars, now they've discovered a planetary system, in fact several now since I wrote this talk, orbiting a double star, what they call a circumbinary planetary system. Now, planetary climates in such a system would be, well, to be frank, crazy. There would be huge short-term temperature changes as the stars themselves eclipsed each other, such that a potentially habitable planet would feel like it had seen summer through winter many times during a single orbit around its pair of stars. Next one, please. Then it turns out that many exoplanetary systems are crowded in really close to their central stars. And I mean crowded. If you look at this example here, you'll see that this real system here around the star Kepler is actually within this blue cylinder and is only just larger in terms of orbit size for these multiple planets than the size of the orbit of Mercury in our own system. So crowded really means crowded in many of these systems. Next one, please. Okay, good. Now, by various feats of scientific excellence, which I won't go into here, astronomers can now determine the size, the mass, and therefore the density of exoplanets. And in turn, and it turns out that in numerous examples of exoplanetary systems, not only are the planets crowded close to their central star, but some of the closest are the size and makeup of Jupiter, or even bigger and significantly bigger. The model of planetary formation, which I do not fundamentally question, and I will discuss in a few minutes, makes it absolutely clear that these hot Jupiters must have formed much further away from their central star than where we see them now. So they must have migrated inwards towards the star. And in so doing, they would have eliminated all the planets that had formed in the inner part of the solar system, either by driving them into the central star or by booting them out of the planetary system and into interstellar space. Such orphaned or rogue planets have already been detected roaming between stars in our galaxy, by the way. All I can say is this: thank goodness Jupiter stayed where it is. Or did it? More on that later. Next one, please, Chris. Astronomers Astronomers have also determined that unlike our own solar system, many exoplanetary orbits do not lie close to the equatorial plane of the central star, the ecliptic plane that planetary orbits of our solar system approximate to. Worse, as opposed to our solar system where all the planets orbit the sun in the same direction, in the same sense that the sun spins on its own axis, some exoplanets rotate in the opposite direction. That is to say, they have what are called retrograde orbits, but there's as yet no full consensus on why. However, one obvious possibility is that they were captured from a close passing star and its own planetary system. How's that for unpredictable instability? Next one, please. Now, put all this together, and it turns out that crowded, non-equatorial, retrograde orbits and close-in gas giants are to be expected, as opposed to being exceptional. Next one, please. And if this wasn't complicated enough, it turns out that many exoplanetary orbits are both markedly elliptical and eccentric with respect to the central star, as shown in this representation of an eccentric exoplanetary system compared with our own solar system. Our own solar system here is indicated by the dashed lines, and the idea is that our star is in the middle there. And the full lines here for B, C, and D, these are the exoplanet orbits around the star Upsilon Andromedae. Andromedae, thank you. So my take-home message regarding exoplanetary systems is this. They tend to be dynamically complex swarms. They're commonly crowded. They're highly unstable, with giant planets playing cuckoo and booting potentially habitable inner planets out of the nest. Next one, please. All of which now brings us to our own solar system. Now remember, from 15th to 16th century Copernicus to about a few years ago, astronomers thought of our solar system as the epitome of stability. Little did they know. Next one, please, Chris. But you can see why readily. All of the elements of our solar system, approximately scaled here for size, from planets to asteroids to comets, can be represented in an image such as this. But this does not really tell the story. Next one, please. This is a better representation, inasmuch as it emphasizes the division of the solar system into inner rocky planets, those that we know and love, from Mars out to Mercury, or into Mercury, and the outer gas and ice giants. And here we've illustrated the moons of key moons of Jupiter as well. But it too is lacking in accuracy. Next one, please. Now this image, while not scaled for distance, underscores the fundamental structure of our solar system. Small rocky planets in the interior, separated from the gas and ice giants in the outer parts by an asteroid belt located between Mars and Jupiter, so located about here. And lo and behold, there's Ceres actually in the asteroid belt. And all of these elements orbiting in the same direction, prograde in the same elliptical plane, equatorial to the sun. I don't mean that all the asteroids are necessarily doing that. It all looks so simple and orderly, doesn't it? Next one, please. Even what's called the standard model for solar system formation and development looks simple. And that model goes something like this. Once upon a time, about 4.5 billion years ago, there was a solar nebula that was hot in the interior and cool in the exterior. Next one, please. The sun evolved in the center of the rotating nebula, and the surrounding gas and dust developed into a protoplanetary disk. During the first 100 million years of solar system history, planets grew in the protoplanetary disk by a process called accretion, for which there are various interpretations among astronomers, but we won't go there just now. And because of the original rotation of the solar nebula, a property referred to as angular momentum, all of the planets orbit the sun in the same direction as the sun rotates on its own axis. Next one, please. Now, the rocky planets in the internal part of the solar system, and most likely the rocky cores of the gas and ice giants in the outer part of the solar system, formed at least in part by the clumping together or progressive accretion of primitive components of the solar nebula known as chondrules. That's these little blobby things here, which you can see here in 3D. You can see in section in both these pieces here. These admittedly weird objects have the same chemical compositions that closely resemble that of the dust component of the solar nebula itself. Next one, please. through a combination of heat generated by the accretion processes themselves, transforming the kinetic energy of the moving material into heat, plus the breakdown of short-lived radioactive elements, the early planetoids heated, melted, and differentiated into what we recognize today as rocky planets with iron-nickel-rich metal cores, thick rocky mantles rich in iron and magnesium, and thin rocky crusts rich in silicon and aluminium. Next one, please. And here are the rocky planets, just to refresh your memory. And if we jump to the next slide. In principle, this process of accretion also applies to the cores of the gas and ice giants. Next one, please. But our solar system includes more than just the sun and its cortege of planets. The sun and the major planets are embedded in a disk of comets, asteroids, and minor planets, known as the Kuiper Belt, itself surrounded by a hollow sphere of mostly comet material, referred to as the Oort cloud. The Oort cloud extends about a quarter of the distance to the nearest star. So we're talking just under a light year here in terms of radius. Keep this nested geometry of the solar system in mind, as we'll return to it shortly when we look at how the solar system evolved in its early years. Next one, please, Chris. I mentioned minor planets just now. These, of course, are the mostly spherical objects that were so important in the recent and controversial demotion of Pluto from major planet to minor planet status. That's an ongoing debate. I'm not going to get into it here. It's best developed over a glass of whatever does you good and whatever keeps you mellow. Next slide, please. Well, until a few years ago, that pretty much was where the standard model for the formation of planetary systems ended, apart from a slight complication at about 4 billion years ago, when a whole load of collisional impacts occurred throughout the solar system, leaving planets and moons with the major scars on their surfaces, craters and multi-ring basins that we can observe today. But I'll explain that in just a minute. Suffice it to say for now that this well-known complication was perhaps the first sign that our solar system had had an exceptionally dynamic past. And as it turns out, the deviations from the standard model include things going backwards, as well as inwards and outwards with respect to the sun, and planets which actually swap their orbits. In short, the current model for our solar system has become rather complicated. And this is what we're going to look at now. Next slide, please, Chris. Now, during the past decade, as astronomers renewed their interest in the solar system, and it is actually fairly recent, they began to realize that there were some intriguing observations and questions that the old standard model for planetary systems could neither explain nor answer. These included, first, the Great Bombardment at about 3.8 billion years ago, when planets and moons throughout the solar system were pummeled by massive asteroid and comet impacts. Why did it start so late? About 700 million years after planetary accretion was over. And why did it stop? Second question that they couldn't answer. Theoretically, Mars, a rocky planet, should have grown to about the same size as Earth and Venus. Two other rocky planets. Mercury is another story. Why is Mars so small? And what stopped it from growing bigger? And the third question they couldn't answer was this. The asteroid belt is made of more or less primitive accretionary debris that never got it together to make a planet. Some people think it was a planet that got broken up. It's not. It's the other way around. It never made a planet. And the questions they couldn't answer are these. Why is the asteroid belt zoned with drier material in the inner part of the belt and wetter material in the outer part? Now, the answers that astronomers have come up with for these questions stem from a computer model, and it goes like this. In the beginning, at about 4.5 billion years ago, while the planets were still forming, Jupiter migrated towards the central star of our solar system. Probably because leftover material in the solar nebula was slowing it down because of friction. As it did so, it interacted gravitationally with the accretionary material that was feeding the growth of Mars, booting that material out of the Martian orbit and thereby stunting Martian growth. Remember, this is a model, a computer model. Observations of exoplanetary systems would have predicted that Jupiter's inward migration would have continued to within the orbit of Mercury. But things didn't play out that way, obviously, or we wouldn't be here talking about it. Instead, something remarkable happened that made Jupiter turn around and migrate outwards again. According to the computer modeling, the remarkable event was that Saturn began to follow inwards towards the Sun, caught up with Jupiter, and developed what's called a 2 to 3 orbital resonance with Jupiter, meaning that Saturn orbited the Sun twice for every 3 orbits made by Jupiter. Planetary physicists tell us that this not only slowed Jupiter's inward migration, it sent both Jupiter and Saturn migrating away from the Sun. Though through a loosely described, or through a loose sailing analogy that Brian McCullough can explain better than I can, this part of the model of planetary migration is known as the grand tack. And as I say, it occurred during the first 100 million years of the life of the solar system. What comes next? Next one, please, Chris. What comes next is still a little fuzzy. It's not that I'm fuzzy on it. I've actually written to the folks that put these models together. They are fuzzy on it. So the fundamental science here is a little fuzzy in getting to the next step. But around 700 million years later, at about 3.9 billion years, the orbital resonance of Jupiter and Saturn evolved from 2.3 to 2.5, meaning that Saturn now orbits the Sun twice for every 5 orbits made by Jupiter. In order to accomplish this, Jupiter and Saturn now migrate even further from the Sun. Well, guess what? Uranus and Neptune made of all this gas giant planetary migration, they migrated outwards too. In so doing, they encroached on the comets, asteroids, and minor planets of the Kuiper Belt and the Oort cloud. As you can see in this image here, all hell broke loose. All kinds of Kuiper and Oort materials were flung both into interstellar space and into the solar system itself, leading to the Great Bombardment at about 3.9 to 3.8 billion years. Pretty much by definition, all disturbances are transient. And when this one was over, the Great Bombardment had gradually petered out by about 3.5 billion. But during the outward migration of the gas and ice giants, something astonishing happened. Here, at about 4.5 billion, you see this purple orbit out here? That's Uranus. And this sort of a bright green orbit, that's Neptune. This, of course, is the Oort cloud and the Kuiper belt. Move through to the end of the Great Bombardment at 3.65, and what's happened? In fact, it happened at 3.9 to 3.8. The green ring of Neptune is now outside the orbit, the purple one, of Uranus. These two planets have swapped orbits, or they've swapped positions. Now, this part of the model, the planetary migration model, is known as the Nice model, after the town in southern France where the scientists lived who put this model together. The physical explanation, the physics behind the grand tack and the Nice model are quite beyond me. I'm just a simple geologist. But maybe the likes of Rob Dick, Al Scott, I can always talk about Al, he's not here, Bob Olson, I know you're there, Bob, could explain it to us one of these days in nice, easy words. In addition to explaining the size of Mars and the timing of the Great Bombardment, all the tossing of interplanetary accretionary debris and comet-like materials inwards and outwards, that is predicted by the model, leads very neatly to the zoning of the asteroid belt in terms of wet versus dry asteroids. A very neat model indeed, but remember, it is a computer model. Next one, please, Chris. So now stop for a moment and consider the significance of this concertina-style model of the solar system, because this is going to be the take-home message for our solar system as a planetary system. Both Isaac Newton and Albert Einstein would agree that two bodies orbiting a third through gravitational attraction represents an inherently unstable system. This is the classic three-body problem. To be blunt, wait long enough and it'll come apart at the seams eventually. Yet here we have 8 major planets orbiting the Sun, and the outer part of the solar system behaves like an accordion, initially contracting and then expanding, with some pretty large pieces of astro real estate being flung into the interior of the solar system if we're to judge by the size of the impact features we see on our own moon. And yet the entire solar system still hangs together more or less in the same orbital plane, in almost circular orbits, for a further 4 billion years. If that's not exceptional, if that's not remarkable, I don't know what is. Next one, please. So let's now look at the solar system components themselves. How predictable are they? First, let's take a look at planet-moon systems in the outer solar system. Next one, please, Chris. Nope, we're there. Good. Hold it right there. Thank you. It's commonly assumed that moons orbit planets in a plane aligned with the planet's equator, and that they all orbit in the same direction. I think one of the reasons this is such a common assumption is the extraordinary case of the planet Uranus. Even though Uranus is unique in our solar system in that its own spin axis is almost perpendicular to that of the other planets and the Sun. In other words, the spin axis of the planet lies in the ecliptic plane. Next one, please. Its multiple moons follow what are called prograde orbits, moving in the same direction as the planet spins in a plane parallel to the planet's equatorial plane. In other words, in a plane perpendicular to the ecliptic. While we've got Uranus and its moons on screen, the most likely reason for their anomalous orientation within the solar system is a collision with something really big that knocked the planet over permanently. Yet another possible cause of unpredictable instability that failed to disrupt the solar system. Next one, please. Now, while it's true that life would be certainly much simpler if all moon orbits were really prograde and equatorial, it just ain't so. Here's a simplified representation of the orbital directions of Jupiter's moons projected onto the planet's equatorial plane. Blue orbits are prograde. In other words, the moons orbit in the same sense as the planet spins on its own axis, anti-clockwise as seen from above, as here. And the red orbits are retrograde. The moons orbit in the opposite direction. Notice how the retrograde orbits are absent from the interior of the planet-moon system. That's because the influences to get things going in the same direction as the planet is spinning increase as you get closer to the planet itself. Notice also that some orbital paths appear to cross over others, but this is more apparent than real if we look at this in 3D. Next one, please, Chris. Now here you see Jupiter, that little yellow dot in the middle, merrily moving around the Sun on its own orbital path in red, surrounded by a swarm of 64 moons, many of which have highly inclined orbits. The retrograde moons were likely formed elsewhere in the solar system and then later captured by the planet. Now, I've commonly read and heard that the Jupiter-Moon system is compared to a mini-planetary system. Well, if it is, it looks nothing like our own planetary system, although simplistic comparisons could be drawn with some exoplanetary systems. Next one, please, Chris. Now, you might think Jupiter is an anomaly in this regard, but it's not. Here's a very similar pattern in the Saturn moon system, with a swarm of prograde orbits in red and retrograde orbits in green. So my take-home message about the largest planet-moon systems within our own solar system is twofold. First, they're highly complex and look nothing like the old, simple mini-solar system model we probably learned about in school. Second, planet formation models tell us that in order to form these hornet nest moon systems around planets, the early solar system must have been buzzing with planetoids and large asteroids going every which way. In summary, things must have been not far short of chaotic, at least as far as the small stuff was concerned in the early solar system. Next one, please, Chris. So what about the planets themselves? Using our growing knowledge of planetology and planetary geology within our solar system, let's take a look at what's normal about a planet, at least the neighboring planets, starting with the planetary interior. This pretty much means we focus here on the rocky planets of the inner solar system, because we can't see the insides of the gas and ice giants. We can only make intelligent guesses. I believe that they are intelligent guesses. Venus and Earth are very similar in size and internal structure. The principal difference between them is as illustrated here simply reflects the fact that we can observe that Earth actually has an inner core. That's the yellow thing here. And there's the liquid outer core in red. And in the case of Venus, we're just not sure yet. Mars is significantly smaller in size, but the internal structure is not very different from that of its sister planets. So let's start with the one we know best, the Earth. Next one, please, Chris. As a geologist, I could talk to you all night about the Earth, but don't worry, I shan't. I've got myself on a very tight rein here. Instead, let me highlight the most characteristic feature of the Earth as a planet, its plate tectonics. I've talked to you about this before, but let me remind you. Thanks to plate tectonics, the Earth has continents that break up, they move apart in response to new ocean floor material being created at what are called mid-ocean ridges. And you can see them here in the Pacific. You can see the most famous one coming down here through the entire Atlantic. And they're all over the place here in the Indian Oceans and the Western Pacific. And the continents can come together in slow motion collisions in response to the sinking of old ocean crust back into the planet's mantle. The sinking of the ocean floor creates volcanic arcs, such as the islands of Indonesia and the Andes of South America. So here are the Andes, and the islands of Indonesia are over here. And colliding continents generate mountain chains, such as the Alps over here, or the Himalayas over here in red. Next one, please, Chris. Now, here's a cartoon, I've shown it to you before, of spreading and sinking showing volcanic activity at both locations. Here's the spreading and there's the volcanic activity. Here's the sinking, more volcanoes out here in the middle of the ocean, or here along the edge of a piece of continental crust. This volcanic activity is what has allowed the Earth as a planet to cool continuously through time. Without this continuous cooling, the Earth would look like Venus. Next slide. Venus is a barren wasteland with an average surface temperature in the 400 to 500 degrees centigrade range. In other words, lead would melt on the surface. Why? Quite simply because it has no plate tectonics. Without the ability to cool as a planet, heat generated continuously by radioactive breakdown of elements builds up inside the planet. This has a number of dramatic consequences, the principal one of which is that the outer part of the planet's mantle, and I mean over hundreds of kilometers depth, melts and erupts, completely resurfacing the planet. In the case of Venus, the low density of impact craters on its surface tells us that this happened quite recently, geologically speaking, certainly within the last billion years, possibly within the last 500 million. Massive, possibly catastrophic volcanism like this pumps enormous amounts of CO2 into the planet's atmosphere. And we know what CO2 can do to planetary atmospheres, especially to this extreme. They go up. Worse, if heat inside the planet cannot escape continuously, the dynamo inside the planet's core that generates the planetary magnetic field stops. For those of you that are as old as me, think of a lava lamp. And without a magnetic field to protect it from the solar wind, the planet will lose the lighter components of its atmosphere as the solar wind strips away hydrogen and oxygen, in other words, water, as well as nitrogen and argon, the principal components of Earth's atmosphere, for example. In the case of Venus, there is a thick atmosphere surrounding the planet, even without a magnetic field. But it's 99% CO2, and it's 100 times denser than our atmosphere on Earth, which is why it resists erosion by the solar wind. Next one, please, Chris. I should have shown you this for magnetic field, but it's just really wallpaper. You can get the point about magnetic field protecting the planet. Next one, please, Chris. And we're on track. Sorry about that. I got carried away. In case you're wondering why Venus has no plate tectonics, it all comes down to water. Venus isn't just dry outside, it has no water inside either. Water has a remarkable effect on rocks, even at very high temperatures and with lots of geological time. Without water in their chemical structure, rocks are extremely stiff and cannot flow. If rocks can't flow, and that includes the rocks that make up a planetary mantle, then plates can't move, and the planet can't cool. You'll find a detailed examination of this issue that I presented here over a decade ago on the RASC Ottawa website under the articles page. And I got to thank Chuck for actually updating that section there quite recently. The URL is actually down here for those in the front that can see it. Sorry, I couldn't put it at the top. The question that planetary geologists are now asking about Venus is this. Did it ever have enough water for plate tectonics in its early history? And if it did, how exactly did it lose it? But that's another question. Next one, please, Chris. One last oddity about Venus. It spins very slowly on its axis, taking 243 Earth days to complete one rotation. And it's the only planet in the solar system that apparently rotates backwards. There are all kinds of theories to explain this. We don't have time to get into them here. Instead, let me emphasize my take-home message that Venus may have been Earth's twin once upon a time, but she certainly isn't now. Next one, please. Now, as a planet, Mars doesn't look much like Earth either. It's about half the size for a start, having been starved during its early accretion. And because it's small, it contained less radioactive material than the Earth, so it cooled quite rapidly. Martian rocks older than the Great Bombardment, at about 3.8 billion, show signs of having been exposed to a planet-scale magnetic field, but younger rocks don't. So we know that the Martian dynamo in the planetary core had shut down by not far short of about 4 billion years ago. And the consequences were dramatic. Without the protection of its magnetic field, the Martian atmosphere was stripped away by the solar wind, even at that great distance, such that today it's 100 times less dense than that of planet Earth. Next one, please. Now, this image nicely summarizes what was known about planetary magnetic fields within the solar system prior to the MESSENGER probe currently orbiting Mercury. What it says is that Saturn and Jupiter have magnetic fields that are respectively 500 and 20,000 times stronger than Earth's, something you really don't want to experience as a carbon-based life form. It also says that Mars and Venus have magnetic fields that are respectively 5,000 and 25,000 times weaker than the Earth's, which is why their atmospheres are either incredibly thin or incredibly dense. In addition, Mercury's magnetic field, frankly, isn't worth writing home about, and certainly is not strong enough to protect an atmosphere of any substance. So my take-home message regarding the inner or rocky planets is this. Firstly, without water, plus plate tectonics to allow an Earth-size or larger planet to cool continuously, the planet will overheat and load its atmosphere with heavy CO2 that will turn its surface into an oven. Secondly, such a planet will also lose its protective magnetic field because it overheats internally. But a smaller planet, such as Mars, will also lose its magnetic field early in its existence because it can't make and retain enough heat for long enough, and therefore it will lose its atmosphere forever. This last point is the primary reason why the science fiction concept of terraforming, which I'm sure you've heard about, terraforming barren planets like Mars, will never be a realistic proposition. Next one, please. So to round out our comparison of rocky planets, tiny Mercury seems like the odd planet out. Although it's only as big as Jupiter's moon Callisto, it's so dense that its iron-nickel core must occupy 80% of the planet's volume, potentially calling into question the universality of the standard model of planetary accretion and differentiation. So here's the bad news. Despite new data from MESSENGER, currently orbiting the closest planet to the Sun, we still do not have a clue as to how Mercury ended up like it did. Stay tuned. If they ever find out, I'll let you know. You'll be the first to hear. Next one, please, Chris. Now, I'd like to look specifically at what makes the Earth the pleasant planet that it is. And to do this, we have to look at how things rotate. Or rather, no, how things that do rotate, like planets, wobble. Or if you want to get technical about it, how they precess. Next slide, please, Chris. The concept of precession is best illustrated by reference to a gyroscope or to a child's spinning top. But the same basic principles apply to planets too. In this example of a spinning gyroscope, the axis of rotation itself precesses as it describes a circle. And in this particular case, I can't tell which way it's precessing with respect to the overall spin. Next one, please, Chris. Planet Earth does something similar. Over a period of about 26,000 years, the rotation axis of the Earth precesses or wobbles. Why is this important? Next one, please. It's important for two fundamental reasons that help explain why Earth is such a pleasant planet. First, the tilt of the Earth's axis with respect to the ecliptic plane of the solar system, about 23.5 degrees at present, is what produces the annual cycle of the seasons. For example, here you see the Earth's axis tilted with respect to the Sun, which lies off the screen to the right, such that more sunlight falls in the southern hemisphere, which experiences summer temperatures. Second, this is the important part. This is a very stable, long-term configuration on the scale of hundreds of millions, possibly billions of years, which means that the climate zonation of the blue planet remains stable even if climate itself changes over the shorter term. In other words, A new period of global glaciation will always start in the polar regions of the planet. Next one, please. Compare this with the behavior of the Martian spin axis that shows variations of up to 60 degrees or more, over much shorter time frames of the order of 100,000 to 10 million years. You can imagine the impact this has on long-term climate stability for the red planet. For example, with enough of an extreme tilt of the planet's rotation axis, glaciation could start near the equator. Next one, please. The rotation axis of Venus, despite the artistic camera angle shown here, is practically perpendicular to the ecliptic plane. In other words, wobble is not an issue here. But remember, it's formally upside down, which adds yet another twist to the planet of love. As for Mercury, it too is practically perpendicular to the ecliptic plane, with the rotation axis tilted at just 7 degrees. Next one, please. Why is consideration of axial tilt and precession key to discussion of what makes for a pleasant planet? A place where you would want to live, raise your kids and your grandchildren. Why have I gone into this much detail here? Well, for two fundamental reasons. First, life and the evolution of life as we know it requires long-term climatic stability. Not long-term weather, long-term climatic stability. Second, life as we know it requires clocks to know when to sleep, when to grow, and when to reproduce. And those clocks on Earth are provided by the diurnal cycle of night and day as the Earth spins, and by the annual seasons as the tilted Earth orbits the Sun. A recent report by German scientists indicates that a planet with a tilt of less than 5 degrees would develop extreme temperature gradients between a hot equator and its frigid poles, and that zero tilt would lead to thermally driven total collapse of the planetary atmosphere. So, okay, if stably precessing tilt is also fired important, how come Earth has it and Mars doesn't? And the answer is the moon. Next one, please, Chris. Our moon is weird. First, if you compare the size of each and every moon in our solar system with the size of the planet that moon orbits, you'll find that our moon is anomalously huge. Huge, relative to the home planet. Second, because it's large, compared with its planet, it exerts an anomalously strong stabilizing influence on the precessional behavior of the Earth. Next one, please. But here's the really weird part. Planetary theorists have interpreted our moon as the product of an unpredictable, accidental, dare I say random, collision of early Earth with a Mars-sized planet that produced a ring of debris that coalesced into the moon that we see today. There's some discussion as to exactly how this collision model works. In recent time, there have been some questioning of it. I think it's now been re-established, but we're now talking perhaps about much larger colliding objects than we were talking about 2 years ago. Next one, please, Chris. We can skip that one. But there's a third reason why I want to address this issue of tilt and precession. Astronomers are currently looking to find Earth-sized rocky planets orbiting central stars in what is referred to as the habitable zone. This refers to a disk-like zone wherein liquid water is stable. In other words, it neither boils off as steam nor freezes as ice on the planetary scale.
Is that the Goldilocks zone?
You could call it the Goldilocks zone as well. They calculate the location and width of this zone principally from the size, temperature, and brightness of the central star. And that's it. But as we've just seen, the tilt of the axis of rotation and its stability is critical to the existence of a pleasant planet. In short, put an Earth-sized rocky planet with zero tilt in the habitable zone, and it may not have a stable atmosphere. Hardly habitable, if you ask me. Alternatively, put a precessing tilted planet in the habitable zone without an anomalously oversized moon to stabilize it and see what kind of long-range climate you get. Let me emphasize, the Earth is not a Goldilocks planet. Not too hot, not too cold, just because it sits in the sun's habitable zone. Its precessing tilt stabilized by our moon is an essential component. Next one, please. Okay. As we draw this talk to a close, all good things must come to an end. It's time to explicitly address the three questions that I asked at the outset. I'll do it quite briefly. Next one, please, Chris. So, is our galaxy representative of galactic environments within the universe as we know it? Well, there are billions of galaxies, and many of them are or have been in some form of turmoil or another. But there are many pleasant galaxies, even large spiral galaxies just like our own, that appear to have enjoyed extended periods of calm and quiet, such as we hope we are, and will be quite capable of providing a suitable environment for a pleasant planet such as the Earth to develop in. So let me rephrase my question slightly. Is our galaxy weird or special in some way? Is it a rare occurrence? And the answer is clearly no. Our galaxy is pretty normal as barred spirals go. Next one, please. So is our seemingly tranquil and stable solar system really representative of planetary evolution? Is it a blueprint or is it a special case? Now, although we've only just started to sample exoplanetary systems in a small corner of our galaxy, we can already see that our solar system is far from normal. Our planets follow near-circular, prograde, near-concentric orbits in a common plane. Many exoplanetary systems don't look anything like this. Our planets are what I describe as comfortably spaced. In many exoplanetary systems, they're crowded around the central star. Our planets are systematically distributed, with smaller rocky planets close to the Sun and gas and ice giants further out. Newly discovered exoplanetary systems are showing that this is not universal. They're actually finding alternations of gas giants and rocky planets, gas giants. Many exoplanetary systems show evidence for disruption as gas giants migrated inwards and eliminated the inner planets. Jupiter began to do the same, but got dragged back outward again by Saturn. Even a simple system made of one star and two planets is inherently unstable over the long term. Yet, after Jupiter's inward migration, the subsequent outward migration of all gas and ice giants, the resulting great bombardment when everything went every which way, as the Kuiper Belt and probably our Oort cloud got stirred up, Uranus getting bowled over on its side, probably by a massive interplanetary collision, and Uranus and Neptune switching orbits, our solar system has remained stable for 4.5 billion years. I have to conclude that no, our solar system is not normal. It's certainly not ordinary. It is certainly very special. Next slide, please, Chris. So the third question, is our planet really representative of a habitable world in a planetary system? Again, is it a blueprint or is it a special case? Well, we've already seen that it's not enough for a rocky planet to be located in a planetary system's habitable zone to make it a pleasant planet, which I think you all agree Earth is. In addition, it must possess an efficient and effective means of continuously cooling the planet over billions of years. I mean cooling the planet interior, on which on Earth is provided by plate tectonics, which is unique in our own solar system. A magnetic field is required to protect the lighter components of the planetary atmosphere, nitrogen, oxygen, argon, hydrogen, from the solar wind, which Earth has thanks to its size, compare that with Mars, plus the fact that it has plate tectonics, compare that with Venus. It also needs a moderate axial tilt that generates predictable seasons and a mechanism to guarantee the long-term stability of that tilt for hundreds of millions, perhaps billions of years, even as it wobbles or precesses. And Earth has an anomalously large moon compared to the size of the planet, which provides that stability. So no, I don't think we can say that the Earth is normal. There are lots of very special conditions that go to make up our place in the solar system and the place of our solar system in our galaxy. Finally, here's another question. Is the Earth unique as a planet? That's very different from asking if it's special or normal. Is it unique? In light of the billions of stars in our own galaxy and the billions of galaxies estimated to populate the visible universe, it would be unscientific to claim that similarly special circumstances could not combine to create a similarly pleasant planet somewhere else, be it in our galaxy or beyond. But I really wish this is something the professional astronomers would be more explicit about when they're discussing this topic, especially in the media. I do think that we can conclude that planets resembling the Earth do not occur in every nook and cranny of the galaxy. They don't occur at every street corner. Fundamentally, nature doesn't make them like that just any old how, any old where. Next slide, please, Chris. So my final take-home message is this. Astronomically speaking, the Earth is probably not unique, but it is very, very special. Thanks for listening, and a very happy end to the year of the solar system to you all.
We'll open the floor for a few minutes for any questions. Go for it, Chuck.
Okay, yes, Simon. Brown's book, Rare Earth, sort of touched on the galaxy part of your talk. And he stated that we're sort of situated in a kind of a blank area of the galaxy. So we're not close to the big guys blowing up and all the other radiation. That's part of our specialty, I guess.
Well, even though our galaxy is nice and quiet and tranquil, it doesn't mean there aren't all kinds of things popping off within it. By tranquil, I mean with respect to collisions with other galaxies or the black hole in the center. It's just as well that we're a reasonable distance away from supernovas, because over the last 4.5 billion years, they would have actually sterilized the Earth if they'd been in too close. So that adds to what's special. But there are all kinds of other bodies out there that are probably also at equally safe distances from them. It really is the cumulative look at what's special about our solar system. Our galaxy is not, but what's special about our solar system. And boy, we've been through a really weird evolution. And then the actual situation of the Earth itself, plus its moon, of course, and its plate tectonics, and its tilt. There are just so many variables that lead to our very special case.
Simon, we know that the solar system, the sun with its planets, rotate around the galaxy. What's to say that as we rotate, we do not run into or get close to another large star, which would probably create havoc in the solar system, even at, let's say, 1 light year away or 2 light years away?
It's a very timely question, Paul. There's been some chemical work, I do not recall the details of it because I haven't looked at it in a while, on cometary chemistry, suggesting that some of the cometary material in our solar system has actually been stripped off from another solar system. In other words, we have had close encounters. I didn't want to get into this because we don't really know anything about when they might have occurred, how many there might have been. Was it just the one? It's a model. It's a chemical model. Are they even right? But the chances are that throughout our history, there have indeed been these kinds of encounters. So again, the stability of our solar system is quite extraordinary. But I don't know what the statistics on those kinds of interactions might be.
Yeah, I guess further on that, because the tidal radius around a star is sizable, it doesn't take an extremely close passage of, say, 2 Oort cloud systems to intermingle and, for swapping of cometary bodies to occur.
Yeah, Glenn's pointing out that when you're looking at the solar system, you don't just look at the material stuff in it. If you actually look at the gravitational sphere of influence, it's much larger. And that would apply, of course, to a passing star. It wouldn't just be the star, it would be the star, its cohort of material going around it, and its gravitational field. So these kinds of interactions could be common, could be.
Yes, Simon, as you know, I'm a student of biblical cosmology.
And I know you asked me a question based entirely on science.
And I'm in correspondence with a lot of scientists who are astrophysicists, who are also biblical cosmologists and so on. And I'm amazed at your lecture here as to how many correspondences there are between your lecture and biblical statements. So I'm glad to see that our 2 worlds are coming closer and closer together, because we do believe that our Earth is very unique. And in fact, I could just show you hundreds and hundreds of astonishing coincidences of our planet, the uniqueness of our planet, the uniqueness of the moon that you mentioned, and the uniqueness of the sun. In fact, of all the billions of suns that we know, there is no sun that we have seen yet that is exactly similar to our sun. So tell me, I'm just wondering, what is your view of the divine? And do you think that all these millions of coincidences just happen by accident? Do you really think that all these things happen by accident? Or do you think that, as Einstein said and as Newton said, you quoted both of them, they both believe that a divine hand was involved in this?
What Einstein said was that God doesn't play dice, and what he was talking about was quantum physics. And in fact, it turns out that God does play dice because quantum physics actually has stood up to scrutiny. My perspective on accidents, when you actually look at the physics involved, you look at the statistics involved, what you actually get are random events. They're not accidents. If we knew everything about every particle as Newton originally thought, if you did know everything about every particle and the history of everything in our galaxy, we probably could actually work out exactly how things came together. But the essence of science is observation, measurement, repetition of those same experiments, and then moving forward towards modeling which is then predictive. And if the predictive models are able to actually predict what we're observing, you can start to have some confidence in them. All it takes is one more observation to show the model doesn't work, and it's back to the drawing board. But that is the essence and the nature of science, divine or not.
Simon, I actually have two questions. The first is on your closing statement. The Earth is unique. It's just a matter of time before we do find another planet like the Earth, is what you're saying in that statement, right?
Let me rephrase your point. The point being made is that the Earth is not unique, as I'd said, and eventually we will find another Earth-like system. Given the limitation on the speed at which you can do anything, speed of light, this could become purely philosophical. Supposing there is another Earth on the other side of our galaxy,
And the other part is...
we're not going to know about it.
The other part is the gravitational constant hangs very important in everything you've said here. If the gravitational constant were actually different in other parts of the universe, it would throw everything else out, wouldn't it?
Yeah, but the only serious proposition for variation in the gravitational constant, and it's very much a minority view, is that at the scale of bodies the size of galaxies, as you go from the inner part of that galaxy to the outer part of that galaxy, that the gravitational constant may change, and that might then account for the variation in speed of objects orbiting the center of the galaxies, which currently the majority view suggests that there's a thing called dark matter, which we can neither see, smell, touch, or hear. And that's a bit of a shock when you consider that the majority of the universe is considered to be something we can't actually touch.
Are you saying the gravitational constant is different?
No, I'm saying there is a minority view, essentially put forward by a professor of astrophysics out of Hebrew University, which has suggested that you can actually account for the orbital characteristics of galaxies if, at the scale of matter, at the scale of a galaxy, if there is a variation in gravitational constant, but it's localized.
Okay. Thank you.
And it's very much a minority view.
Okay.
Time for one more in the back.
Yes, Simon, you've been essentially some of the points you've been raising are actually only come into fruition or thought about in the last decade or so. And that's rather intriguing because even when it comes to the biochemistry, we're starting to realize that even life itself, what we have here on the Earth, could actually be very rare. Whereas there are other biochemistries around in the studies of extremophiles and so on that actually push that envelope even more. So it's not only that the Earth may be a relatively rare event, but also life as we see it here may be rare. The life itself may well be, you might be able to find them on other worlds, but not necessarily with our biochemistry.
Well, there's an interesting model. So much of astrophysics is models. And a really interesting model was published about 3 months ago, which suggested that, in fact, during interactions of star systems, it would be possible for a passing star system, which actually already contained the seeds of life, to pass them off. Now you say, well, hey, this is nothing new. We've known about this. It's even got a name. Fred Hoyle came up with this called panspermia. And this is true. But every time anybody did the calculations, the speed at which the star was supposed to pass us was such that nothing would actually get from them to us or from us to them. I forget the details, but somebody came up with a justification for moving star systems much more slowly. And if you do this, it then turns out that the statistical probability of exchange of particles between the two solar systems goes up enormously. Now, the consequence of this was, and this is just exchange. You don't know which way the exchange has gone. And the conclusion of that paper, and it's only one paper, said, look, if this is anywhere near true, then this swapping of material may be very, very common between star systems. And if that is the case, then this concept of panspermia may be universal. Take it or leave it. This is the beauty of science. Somebody comes up with another great model until somebody comes along and knocks it down. I wouldn't have raised this if you hadn't actually put the one on the table, Rob.
Thank you. I'm going to ask you not to go anywhere for a second. Simon, I've known Simon for a few years now, and Simon is like an elusive particle, like a neutrino or Higgs boson. So while I've got him here, I'm going to take care of a piece of business that, because of his elusiveness, has eluded us. It is my great pleasure, Simon, to present you with an overdue award as Presenter of the Year for the best talk of last year. So this year is still up for grabs, but we've been trying to get a hold of this guy, and congratulations, Simon.
Thank you all.
I
much appreciate it.
Thank you for an excellent talk.
Thank you.
Wonderful. All right, is Jim here? Jim would just like to give us a couple of words on SmartScope.
This is SmartScope. I wanted to show you that I can take pictures too. I went to Paris to take this picture, and this tower got in the way. So the moon is not that good. But anyway, I'm still making the effort. A couple of things on SmartScope. We're still alive. We're still moving. We've dealt with two issues this month. We've got rid of the old camera, the Apogee 7 that we bought in 2000. I phoned California to ask them about it, and they said they wanted $500 to look at repairing it. We had it for 13 years and never got it to operate. So we've decided to get rid of that, and I'm talking to council now about getting a new camera. I don't know a thing about cameras, about CCDs, so I'm relying on their expertise. We're talking about it for perhaps next year. Right now, it's training. All the mechanicals, the electricals are there for SmartScope, and a couple of our members have been playing with it. Wolf Luncher and I went out 2 weeks ago and basically threw the software into panic. We don't have anything working, so we've asked expert members to come out again, hopefully this week or the next week, including Paul, and see if we can get it working again. And then we'll start training our members. We were trying to transition from the technical side, the technical side of getting everything running to an operational side. So the idea being that we take the technical people who have assisted us so far and give them the operational experience. We can have 4 or 5 key people who know how to run it, and then we'll keep bringing new members such as yourself out occasionally and brief you so we can have a running team of expert operators. Anyway, that's it. Thank you very much.
Winter solstice at the museum there. We are looking for some volunteers for the winter solstice event. So if you've got your authorization and you are looking to help out in any capacity, we would welcome your presence there.
As well as outdoor observing, and time is from on the 21st from 7 to 9 p.m. Did I miss anything on that, Chris?
It's last day of the...
Oh yes. I remember when I first took this podium in January, I said that, December might be my last meeting and our last meeting. So it's a countdown, folks. December 21st. Are you ready for the end of the world?
Yeah.
I may only have one more meeting to go. That'd free me up with some time. Anyway, we'll see what happens. We still got about 7 weeks for that. Good stuff. Eric, Eric wanted to just have a few seconds of your time
Just a few
here.
seconds, just to let you know, we're all updated on DVDs. I had a busy summer, so I caught up on the editing. All of the DVDs are available up till October in the library. If you remember, you can sign them out. If you've done a presentation and you want a copy, just let me know. You can approach me here, or I'm also on the directory list, so if you want a DVD, just email me. Did anyone get all that Simon said tonight? I got most of it, but not all of it. That's why we've got these. We preserve everything that he says on these. Thank you.
Thank you, Eric. All right, just a few wrap-up notes. Estelle's pick of the month, and I know you're here, Estelle. Aurora Watchers Handbook. This might be very timely. We are starting to see increased auroral activity, and we're expecting that to increase even more in the coming year as we reach solar max. Post-meeting, yes, Estelle's here. Al is not. Coffee outside with Art and Ann. Also, who's got calendars? They're out there as well? Okay, good. And we will have our meeting at Kelsey's for those of you that are interested. And yeah, there we go. 122. And I thought we had a good attendance tonight. Thank you again.
It says 132, but I haven't changed the slide.
Really? Oh, okay. Well, there we go. 132. Thanks again for all contributors there for the excellent presentations tonight, and to the museum for having us. And I think we have one more slide there. Yes. So just a final reminder, the dinner meeting is in 2 weeks from tonight. See Gary if you're all interested for tickets. The next meeting for our center, November 30th, 4 weeks from tonight. And we will have our annual swab table just in time for either for Christmas or for the end of the world. You know, they're both in around the same area there. So just to remind you there. And also, Chris reminded me again. I should be reminding you folks periodically. If you do have something that is of interest to you that you'd like to come up and talk about, and I've actually had a couple of people approach me independently in the last couple of weeks. If you do have something that you'd like to present, feel free to come up and talk to us. We'll help you organize a presentation if you haven't done it before, and we would welcome your view on things astronomical and space related. You can send ideas to either myself or Chris. My email address is down there. And I think, is that it? That's it. That's it, folks. Thank you much, and we'll see you in 4 weeks. Bye-bye.